Okay, guys, let's start. I think the last session where I left is here, the different uh, potential energy surface for different reaction, like thermoneutral reaction, then exergic reaction, and endoergic reaction. We, uh, we tried to figure out how the contour plots of different reactions are uh, going to depict the potential energy surface. Okay, so this was the for the thermoneutral reaction. So that is kind of H plus H2 reaction, giving again H2 plus H, right? So that is the same, this energy and this energy exactly similar, and then we are climbing up the saddle point at the middle of the reaction path and going to go to the product. And then this was a exergic reaction where uh, the saddle point comes early, so that means that is near the reactant zone, right? So that is the saddle point. Now for endoergic reaction, of course, it's the other way around, where the saddle point is going to be in the production. So reactants are here, start go further, and then the saddle point appears near the product zone. Right? So these are the three reactions we have looked at. Now these three we can for little bit better clarity, if you want to just put it in that all three of them in the same uh, picture with the uh, potential energy curve, that might give you a little bit more idea. So it is something like this reaction coordinate. So that we are going from reactants to the products. This is the potential energy. Now, if we look at very carefully, like thermoneutral reaction is a black curve, right? So reactants and products are at the same energy level, right? And if you look at here, the transition state, of course, it appears in the middle of the reaction point, right? Okay, now if we think about the endoergic reaction, this one, then in this case, the product's energy are above the reactant's energy, and we realize that the transition state, which is here, so that is this is the transition state, and that is going to be appearing in the late towards the product. So this is called the late barrier. Right? On the other hand, in contrary, for the exergic reaction, where product's energy are lower than the reactants, in that case, the tension state or the saddle point, which is going to be in the entrance channel, that is in the reactants zone, right? So the difference basically in these three are that we are having for the exergic reaction. So the barrier top, that is the saddle point, is near the reactants zone. For the thermoneutral reaction, it is in the middle of the reaction path, and for the exergic reaction, it is going to be at the products zone, right? So with this much introduction, along with the previous class for the potential energy surface, now I guess we are ready to explore the dynamics on the different surfaces. Okay, so I would like to just give you a brief introduction about the dynamics now. Okay, here we go. What we have, I think I started with this because you have like quantum chemistry class, we have a classical dynamics. Dr. Mishra, I think, told you how to solve the equations of motion. Now, this one is the very first classical dynamics, what do we call the Newton's equations. So here, mass m is the mass of the particle, xi is the coordinates, Cartesian coordinates, and that is basically mass into acceleration, that is nothing but the force. Right? So that is the relation. Now, for a conservative systems, uh, the conservative systems are those for which we can derive the force from the potential exactly. Of course, with the relation is that the negative derivative of the potential with respect to the coordinates is nothing but the force. Right? Now, this if we have this system, right, then we can equate this Newton's equation like this. This mass into acceleration, which is force, is nothing but the uh, first derivative of the potential with respect to coordinates, right? Now, this is a second order differential equation. If we integrate twice, so this is known from your potential energy surface. That's what we discussed the potential energy uh, before this dynamics. Right? So this is the potential energy surface. So if we have this potential energy surface V, and then if we do the derivative, that means potential energy, if we do the derivative with respect to Cartesian coordinate, take the negative of that, that is nothing but force, and that can be equated with the mass into acceleration. Now this can be integrated twice. First, if we do the integration, we get the velocity. This part is known, so this, if we do the mass, is of course known for particle. Now, if we do the derivative, then we get this equation. Now, if we do the integration twice, first integration gives me a velocity, that is dx by dt, and if we further integrate it out, then we are going to get xt. That means the coordinates with respect to time. Now, this is nothing but your trajectory, right? So that is this is if we know this, this is nothing but your trajectory. So what is trajectory then? Trajectory is nothing but the coordinates of the system with respect to time. Right? Okay, so that is the simple way to do the Newton's equation and in the classical dynamics of this is not quantum dynamics. So, because you know what are the deficiency of the classical dynamics. Now, in the reality, of course, you should know by now because there are some constants in the Newton's equation. Which, again, if we go back to the classical dynamics, which was discussed in the first part of the quantum chemistry class, is that this is dependent on the Cartesian coordinates, and sometimes we have difficulty in defining the coordinates for the system, uh, like the angular motion. We really have difficult to solve this Newton's equation, right? So therefore, in reality, what we do, we go for Hamilton's equation of motion. So that is because this is first thing is that these are going to be the first order differential equation with respect to the coordinates. Now here, of course, like I should mention here that this qi is for the generalized coordinate. It can be adapted for any suitable coordinate for any system, right? So therefore, the first advantage of the Hamilton's equations of motion is that this can be written in terms of a generalized coordinate. And if we write this, if we have Hamiltonian, which depends on your generalized coordinates and generalized momentum, then we have the first order differential equation, and that is easy to solve it, or easy to integrate it to get the um, trajectory, right? And these are the equations for Hamilton's equations of motion, these two. Now, when the system develops in time, then we solve this according to this equation. So this is position or the generalized coordinate at time t plus dt. Here I'm taking the reference time t0 plus dt. That can be obtained from the qi at t0 plus the derivative of the Hamiltonian with respect to momentum into time, right? Exactly in the same notion, we generate the momentum also like this, right? I think this you are quite familiar with this, so I'm not going to go into the details. Now, so after solving this, what we get is the coordinates with respect to time, right? So therefore, now we have the potential over the whole space, and then if we take this coordinates and superimpose over the surface, right? What we get is that an idea how the reaction is going to proceed. Right? Okay, so without getting into much details, what I would like to pictorially describe how the trajectories are going to evolve on the surface. Okay, so here is the reaction, which I think, if you recall it, we discussed in the, I think, towards beginning of the classes, second, I think second or third class, where we discussed is an exergic reaction. What was the disposal of energy, right? Whatever the energy is exposed, right, because of this reaction, where does that energy go? Right? So that was chlorine plus HI and giving HCl. Now HCl being much more dissociation energy than HI, so this is going to be an exergic reaction. Right? So reaction is reactants are here, and products are here, and this is the reaction part we're going to look at. Right? Okay, now if we look at this, when you solve the trajectory, this indicates how this trajectories are going to give you the products, or not going to give you the product. So that means I'm going to have two different kind of trajectories. First one, if you look at this red one, which you can see that this is going from reactants to the product, right? So I'll discuss it. What is this motion? That is going to give you the reactive trajectory. Now the blue one, what do you look at it here? Starts here, goes like this and bounce back. So this is going to be a non-reactive trajectory. Okay, so let's discuss one by one. Now what we discuss is that, like, look at, if you look at this trajectory, right, this is giving that if I want to have a reaction, and if this trajectory represents I'm having a motion along this, so that means this is going to be kind of a translation motion. So higher energy in the translation mode. So translation is going to look at the red curve, which is the trajectory. That means how the reaction is going to move. So one thing you have to remember, that reaction really does not follow the minimum energy path. Right? It depends on the initial condition. Reaction minimum energy path goes like this. Right? So let me draw this for you guys. So the reaction path, if I take, let's say this blue curve. Yeah. So this reaction path, minimum energy path, is actually starting like this. Is going. This is the saddle point, climbing up. Saddle point again. It is going down, going down, going down, and finally it is going to the products, right? So that is the minimum energy path reaction is going to follow. But you should realize that this minimum energy path is not really followed by reactions. Right? So that is in reality. And so look at the red trajectory. So that means I have plotted the coordinates along the time. Now, red trajectory, you can see that this gives you the motion along this. So that means it is the relative translation energy is high. So that means chlorine is coming towards HI, center of mass of HI, with the high relative translation energy. That coordinate is moving very fast. So that means translation energy is high for this trajectory, and the, this translation energy leads to the product on the other side. Because if you remember this, what we realized, that the exergic reaction, we start with the initial translation energy, and then finally products are going to be vibrationally excited. So we did in terms of the identifying the nascent HCl with the experiment. What we found, that the nascent HCl was vibrationally excited up to V equals to 4. Right? That's what I think you remember. Now here you see that this red curve is the initial translation energy by translation. Now, to compare this very crudely, don't, it's not exactly. Let's say I'm throwing a ball over this potential energy surface. Now, how the potential energy surface look like? Now, here is the transition state near the reactance zone. Right. So this is let's say 0. I'm climbing up, small barrier at the entrance, and then again going down. So this is going to be much deeper. Right? So now if I am throwing a ball with a high translation energy and assuming that molecule is in vibrationally 0 level, so then what happens? Ball goes in over the saddle point with the high translation energy, hits on the repulsive wall of this, then make a move along this. Again, this side also repulsive wall, and move like this repulsive, and then make a move like this, right? So this was translation motion. Now if you are in this product zone, now what is this motion say? So that means it is doing like this. So that is nothing but the vibration of HCl, right? So if we start with the reactants with translation motion, then products ended up with the vibrational excitation, right? So that's what we had discussed based on the experimental observation, that we trapped the nascent HCl, and we found that the HCl was vibrationally hot. And here also the trajectories are also, text is also going to depict exactly the same thing. Okay. Now look at the this blue curve. This one. This is also another trajectory. Okay. Now if you look at here, you will realize that this motion is along this, right? So that means it is kind of vibration of the HI, right? So instead of having the energy requirement in the translation, which is rate up, if we give the vibration, right? So that means we are vibrationally exciting HI, and relative translation is low. Then what happened? This ball, let's say, as if that we are throwing the ball is like this wall, then going to the other wall, and going there. Then it bounced back before this saddle point. Saddle point is little high, and then it comes back to the this reactance zone. Right. So therefore, this is a non-reactive trajectory. Right. So this trajectory non-reactive. Writing is difficult, so that is anyway. You know, you understand this is non-reactive trajectory, and the red one is going to be the reactive. Okay. So what does this finally says is that if we start this exothermic reaction with a relatively high translation energy, then the reaction goes over the saddle point, and finally the products are going to be vibrationally hot. On the other hand, in contrary, if we start the reaction with a vibrational excitation of HI, right, whatever the required energy, then what happens? It bounces back and its reaction does not take place. Right? So that is the idea we get from the classical trajectory. Okay. Now, what happens? We go for the endoergic reaction. Now, look at the endoergic. This is an endoergic reaction, F plus HCl. Here, reactants are here. Look at here. This is the bottom of the well. I'm climbing up along this reaction path. Let me draw it again with a different color. So this one with the pink or purple. Just look at here. Here is the reaction path. Start the reactants going up, going up, going up, like this minimum energy path. Now for endoergic reaction, my saddle point is in the exit channel. So they're near the products, right? So, and then when it cross, again we are climbing down, but it's not as low as the reactant. So this is an endoergic reaction. So this pink curve is the minimum energy path, right? Now, in this case, if we follow exactly the same strategy like this endoergicity, if we give either relative translation or relative vibration or the vibration of the reactants, here it is HCl, are they going to lead you to the product? Let's see. Okay, so look at this blue curve. Blue curve is nothing but giving in this motions, which is nothing but representing the translation motion, right? So if I give you translation, like if I throw a ball with the translation energy, then what happened? The saddle point is here, which is having a barrier. The ball hits on this repulsive wall and comes back to the reactor. So therefore, if you go with the translation, then this trajectory is going to be non-reactive. Right? So this trajectory, which is blue curve, is going to be non-reactive. So this one, okay. This is non-reactive. Okay, so just try to recall is that in case of exothermic reaction, this translation favors the reaction and end up with the vibration, but in this case, translation does not give you any product, so it's a non-reactive. Right. Now, if you go for the other way around, now instead of having translation and as a the required energy, if you give the vibration of HCl and translation being relative translation is low, right? Now that represented by this red curve. Red curve it says motion along this, so that is nothing but the motion of the HCl. So that is vibration. So that means this trajectory indicates is a vibrationally on. Right? So if it goes along this, then what happened? This is repulsive wall. It hit this repulsive wall, and once this repulsive wall, this ball is going to go over the saddle point. Now here no barrier, therefore it goes straight to the product. Right. So what does that means? Now when it goes straight to the product, now this motion is nothing but your translation. So we started with the vibrationally hot, and then it is bounce in this surface and goes straight out to the exit channel, right? So that is H plus HC. So in this case, if we start with the vibrationally hot HCl, and reaction is going to takes place, and finally products are going to have the relative translation energy, uh, uh, having the relative translation, and it's going to be vibrationally cold. HF is going to be vibrationally cold. Right? So in case of endoergic reaction, vibration helps the reaction to go over the saddle point, as this saddle point is in the exit. However, the translation, which is the blue curve, does not help. So if you throw the ball like this, it hits the repulsive wall and comes back. Right. So that is the how the dynamics goes over to different surfaces. Now to summarize this in a better way, I would like to put it in the same curve, same figure, all the consideration in the same figure. Let's see how it goes. Now here you can think about that this column is for exoergic reaction. So the saddle point, you can think about the saddle point in the, this is the saddle point is in the entrance, right? And this column indicates the endoergic reaction. The saddle point is in the exit zone. Yeah. Okay. Now if you go along this, so this is called RD barrier for the exoergic reaction, and this is called the late barrier. Okay. Now we are considering two things. Of course, the total energy for all cases has to be the higher than the energy of saddle point. Otherwise, reaction is not going to take place classically. Okay. So if we think now, the total energy being in such a way that the energy energetically the reaction is feasible, so that is going to give you the reactants, and the reactants are going to give the reaction. Now let's consider we are giving the energy as a relative translation higher than vibration, and vibration, let's say it is going to be v equals to 0. So I'm going to give you the translation motion. So as we discussed in the previous slide, that when you give the translation for RD barrier, is throw the ball like this, it crosses this, hits this wall, and then makes as a vibration motion. Right? On the other hand, for endoergic reaction, right, this is going to hit the repulsive wall, and without crossing this saddle point, it is going to bounce back. Right? So that is the for the endoergic reaction when we are having translation energy higher than the vibration. Okay. Now, if we go to the condition when the required energy or the initial energy, we put it in the form of the vibration, keeping and the translation motion is low. Right, translation motion is slow, so the translation energy is less compared to vibration energy. Then what happened now in case of exoergic reaction for early barrier, we give the vibration along this, and the ball throws like this, it bounce back and come back to the reactant. So therefore, it does not give you any reaction. So this is non-reactive. Okay. On the other hand, if you give for the late barrier, so for the exergic reaction, you give vibrational motion like this, it vibrates like this, hits here, and then it goes like this, it crosses the barrier, and it results into the more like a translation motion, right? So that is going to give you the idea how the trajectories can be studied to decide the effect of the potential over the reaction. Okay, I think it's not that easy for you guys to understand that easily, but you have to visualize this, you have to anticipate this. Number of times more and more you study this, you should be able to figure it out. The reference is given here. You can look at this reference too. So that means reaction dynamics book by R.D. Levin. This is the page number. Okay. Now, with a little bit more, I want to complete this for the trajectories. Now, here what we are saying is that how do we differentiate direct abstraction reaction and compound reaction, or the stable intermediate complex reaction in terms of the trajectory. Right. Now look at here. Here I have plotted the distances, or AB distances, like this. Our AB distances is going to be this one with respect to time. Again, also RBC. Right. So that means initially it is vibrating with the equilibrium. So that's why it is small. Right. RBC. A is infinitely separated. That's why RAB is quite far. Now, when it is coming with a very short period of time, now this, look at here, it is coming, RAB is decreasing, RBC is vibrating near the equilibrium. Now, when it A comes near B, now AB bond is being formed. Now, BC bond is being broken. So, so that means this is the product, this product zone, and this is the reactance zone. Right. Now, the short period of time, what you look at here, the exchange is zone. Right. So that means you can realize that there is no unstable complexes are formed, and a very short period of time, this transition takes place from the reactants to the product. And this takes place within less than a kind of a picosecond. So that is, picosecond is the kind of vibrational motion of the rotational vibrational lifetime of a molecule. So this can understand from the reactant to the product. This is very small time zone, less than picosecond, right? So therefore, this is kind of characteristics of potential which is having no potential well. So it is experimental evidence is that for this is going to be short-lived intermediate complex, right? And that is associated with the potential which is having almost no barrier potential. Which is having no potential well. It is having it can have barrier, but with no potential well, right? And if you recall, then when we did the angular distribution, then this angular distribution is going to be characterized by either forward scattered or the backward scattered. Let's say like so if we plot this in a angular motion, so that is, this is this theta scattering angle, and then if we plot this differential cross section, let's say that is sigma, then we are going to get products like this is 0 degree, right? This is 180. I don't have a space here. So this is 180 degree. This is 0 degree. So you can get like forward scatter, right? Something like is going to come like this. It's not that steep, but it's going to be something like that. Or you can get the backward scatter 180 degree. So that is something like it's going to be like that. So the characteristics of this either forward scatter or backward scatter indicating is that this is going to be kind of abstraction type of reaction, and there is no long-lived intermediate complex is formed, and which is the characteristics of the reaction with the potential with no potential well, right? But you can have the potential variance, no potential variance. Okay. Now, in contrary, if we go for a complex reaction, right, which is having like this, like if we go for um, KCl plus sodium bromide, right? In that case, I'm just going to plot here. Look at here. This is initial distance between sodium and the bromine, so NaBr, and then we are going for the because these are very high, so those are basically products. So this is KBr plus BrCl, right? So so the reactance was KCl actually, NaBr plus KCl, right? Now if we look at this, NaBr is vibrating near this equilibrium distance, and these bonds are being formed, right? So when it's coming closer, bond is formed. Now, if look at here, this knurled motion of the trajectories, right? And this starting from like here, as this is like as if from this point to this point, we are going to have a complex type of form because all bonds are very close, right? So that is something like this structure. So all bonds are being closed. So therefore, we are going to have like something like sodium Br is also closure. KBr is also this one. This one KBr is also near about that, and BrCl also near about that. This one. So that is only possible. This is BrCl only possible if it is going to be a stable complex. So this stable complex have lifetime more than picosecond, right? So it's a few picoseconds. So you can look at here from here to here. Yeah, it got disconnected. But anyway, let's see where we were. Yes. So at this place, what I want to say is that now, unlike direct abstraction, here this is quite stable, and we are going to have lifetime of this complex. Let's say, like if you look at from this to this zone, is quite longer than the picosecond, less than the vibrational rotational period, right? So it's a couple of picoseconds. So therefore, in case of stable complex like this form, we're going to get a snarl trajectory, and then ultimately, finally, it's going to form the product. Now, when this trajectory goes out of this potential well, so this was trapped in the potential well, so that is the signature. Now, when it goes out of the potential well, it does not really understand from which side of the potential it enters. So that means whether it enters from the NaCl and KBr, or it is NaBr from NaBr plus KCl. So it forgets its um, orientation, initial orientation, and therefore we get the experimental evidence of this kind of reaction. What we get is that it's a forward backward symmetric product angular distribution, unlike the previous one, and it's associated with the potential level, right? So the angular distribution what we get is something like this. This is my data. This is 0 degree, this is 180 degree, and we are going to get differential per section. We are going to get symmetric like this, and we get near 90 degree, and then finally also something like this. This almost symmetry, and this is symmetric with respect to that is the 90 degree. Okay. Sometimes, of course, we get kind of isotropic. So that is also that depends on actually the angular momentum distribution. So isotropic maybe something like that. Right. So these are the indication of this, that this is formed, stable intermediate complex is formed, and lifetime is more than the rotational period, because if you it does not remember it, so you know whether it came uh, from like KCl NABR or NaCl KBr. So that's why the scattering is going to be symmetric from 0 to 180 degrees. These are all we discussed previously also. Right? So that is basically gives the evidence of this experimental evidence is the long-lived intermediate complex, and that comes from when we have a potential with the deep potential well. Okay. So that is all about I wanted to discuss with you guys for the uh, trajectory over the potential energy surface. Okay, so I'd like to stop here and discuss further, but now we have to go for the experimental setup. So in the next, I am going to discuss for the chemistry experiment by Ahmed Jal, which gives the real trapping of the transition state complexes, and we will be using the pump and probe experiment. It's quite interesting, and we will discuss in the next session.